Lesson, little advice. I'm going to do a little thought experiment. I'd like you to imagine that we had a cannon. We're going to start, by the way, we're going to start to look at Albert Einstein's theory of special relativity. It should really be called the theory of the special case relativity, and the special case is A is going to be 0. You're going to hear me start to talk about how Albert Einstein realized that acceleration was weird and special. General relativity, his other theory, is the one that worked in acceleration. Special relativity, I can teach you in a few days, and in fact, we'll prove it with Pythagoras, Math 8. General relativity took him 10 years. The mathematics of general relativity, every few years I get eager and I find an online general relativity textbook and I start to dive into it and I start to try and follow the math, and I get about 6 pages in and I go, okay, this is why it took Einstein. But special relativity is not too bad. Why does he call it relativity? Because everything is relative to your point of view, to what he called your reference frame. So we're going to start to imagine that we're in different locations. Are you ready? Suppose we had a cannon that could launch a baseball at 30 meters per second every time. Situation number 1. Imagine Sam is the target and he's holding a baseball glove. What will Sam see? How fast will the baseball be traveling relative to Sam? Well, if it leaves here at 30 meters per second and we ignore air resistance, how fast will it arrive here? Be obvious. 30 meters per second. That's the physics most of you are used to. Okay. Now let's add some relative motion. And by that, I mean, let's put the cannon in a truck. Suppose the cannon is on the roof of a van and the van is traveling towards Sam at 15 meters per second. And then we fire the cannon. Boom! At 30 meters per second. How fast will the cannonball arrive at Sam? What? 45. That's not that crazy. Anyone who's played a throwing sport knows if they take a run and then throw it, their own velocity is added to the velocity of whatever they're throwing, and that's why it goes further. What about if the van was traveling away from Sam at 15 meters per second, and we fire the cannon towards Sam at 30 meters per second? How fast will it arrive relative to Sam? What do you think? 15. Hey, what if we had the cannon and the van going to the left at 30 meters per second, and we fire the cannon to the right at 30 meters per second? How fast will the cannon be traveling relative to Sam? As a number, 0? Is that right? Put your pencils down, look up. So Jordan, here's my question. Do these two answers make sense? You okay with them? Yeah. What if I told you there was an object that did not behave this way? There was an object that, whether it was traveling towards you or away from you, whenever you measured its speed when it got to you, you always got the same answer, no matter how fast the van was traveling. We're going to go cosmic. In the late 19th century, Michelson and Morley, two physicists, conducted an experiment. They wanted to do this van baseball idea with light. And so here was their setup. Look up. They figured if we have light from a distant star, in January, the Earth is moving towards that star in the same way the van was moving towards Sam. And so if we measure the speed of light, we should get the speed of light plus the speed of the Earth, the 45. Not quite as dramatic, because the speed of light compared to the speed of the Earth is pretty minuscule, but they figured they could measure it. They had a clever way of measuring it. And then they figured they would repeat the experiment in July when the Earth was moving away from that star, and they figured, oh, we'll get the speed of light minus the Earth. Got the argument? And so they performed that experiment. So they thought they could measure the difference in the speed of light hitting the Earth in two situations. They figured they would measure the speed of light hitting the Earth when the Earth was moving toward a distant star, and the speed of light when the Earth was moving away from a distant star. And they figured they would get two slightly different answers. So they figured when they were moving towards the star, they would get the speed of light. We usually use a lowercase c for the speed of light. So they would get the speed of light plus the Earth. Moving away, they figured they'd get the speed of light minus the Earth. And then they did the experiment, Jordan, and they got the same answer both times. 30 if we were doing the cannonball. This would be like situation 2 and 3 in the previous example, giving the same answer. Here is the conclusion. Light is special. And the speed of light is a constant for all observers. No matter how you're moving or the light source is moving, whether, Donald, it's moving towards you or away from you, whether you're moving toward it or away from it, whenever you measure the speed of light, you're always going to get the same answer as everyone else, no matter how they are moving. We say this is the most famous null result in history. It's famous for its negative result. They thought they were going to prove something, and it didn't happen. It showed that the speed of light in a vacuum is the same for all observers, regardless of their velocity or the velocity of the light source. The speed of light does not depend on your frame of reference at all. Turn the page. Short version, Mason. Speed of light is a constant. What letter of the alphabet does the word constant begin with? Since the speed of light is the constant, we use a lowercase c as its symbol. How big is the speed of light? Look on the back page of your formula sheet. And we are now on the back page in the bottom section. We're in the relativity section. I think I told you what c is. It's 3 times 10 to the 8th meters per second. You don't need to memorize that, but you probably will because it's a fairly easy one and you're lazy. Okay? So here's the implication. Remember I told you a is 0. We're not dealing with acceleration yet. So if a is 0, d equals vit plus a half at squared just becomes d equals vt. So let's get the v by itself. If speed is distance over time, or better yet, Sarah, let's go cosmic. If speed is space over time, how can we always get the same answer for the speed of light? Well, space and time must change depending on the situation. Only way you can all get the same answer for measuring the speed of light is if space and time are doing weird things. Put your pencils down, look up. Here is what Einstein's aha moment was. He said, look, if light is the issue, let's use light as our timer. Ah, that's clever. So here was the thought experiment he proposed. First, consider a spaceship hovering at rest relative to the Earth. So it and Earth are at rest relative to each other. Suppose the spaceship sends a brief, regularly spaced flashes of light to the planet, as in the picture below. Some amount of time will elapse before the flashes get to the planet. In the same way that it takes light from the sun about 8 minutes to reach us, it would take some time for those flashes of light to reach the Earth. The light flashes will encounter the receiver on the planet at speed c, and because there's no relative motion, successive flashes will be received as frequently as they were sent. So let's do this. Let's send a flash every 6 minutes. Flash, 6 minutes. Flash, 6 minutes. Flash, 6 minutes. And these will go through space, and they'll arrive at the Earth, and the Earth will see flash, start their stopwatch. 6 minutes later, flash. 6 minutes later, flash. 6 minutes later, flash. So in 60 minutes, if we're sending out one flash every 6 minutes, how many flashes will the ship send out? 10. How many flashes will the Earth see? 10. That's the world all of you are used to. Now let's add some fast spaceship motion to it. So when motion is involved, the situation is quite different. Now, the speed of the flashes will still be c, the speed of light. This is what Einstein said. He said you're going to get the same speed no matter what. Whether the ship is moving away from the Earth or towards the Earth, the flash does not get a boost or a loss from the speed of the spaceship. It's not like the cannon on the van. It's not. How frequently the flashes are seen, however, very much depends on the relative motion involved. When the ship travels towards the receiver, Earth gets the flashes more frequently. This happens not only because time has changed due to motion, but mainly because each successive flash has less distance to travel because the spaceship is moving towards the Earth. So let's suppose we set this experiment up, Hannah, just right, so that the spaceship is sending a flash every 6 minutes, but it's closing the distance enough that the Earth is only seeing the flashes every 3 minutes. They're arriving at the Earth 3 minutes apart, clumped together, because the spaceship keeps moving closer and closer to the Earth. In 60 minutes, how many flashes will the spaceship emit if it sends one out every 6 minutes? 10. However, on the Earth, those flashes are arriving 3 minutes apart. So how long will those 10 flashes take to arrive at the Earth if they're arriving every 3 minutes? Not 60 minutes, but we already have an event that takes 60 minutes as far as the spaceship is concerned, but only 30 minutes as far as the Earth is concerned. We have the same event taking 2 different amounts of time. It's going to get weirder, but cooler, but weirder. Now, situation 3, we're going to have the spaceship move away from the Earth, which means the distance is continually increasing. So each successive flash will have a longer and longer and longer and longer distance to travel. And so we're going to set it up, Sophia, just right so that the spaceship is going at just the right speed, so that even though the spaceship is sending out a flash, as far as they're concerned, every 6 minutes, they're arriving on the Earth every 12 minutes. So in 60 minutes, how many flashes will the spaceship send out? 10. But if they're arriving every 12 minutes, how long will it take for the Earth to see those 10 flashes? Not 60 minutes, but 120. As far as the Earth is concerned, the event took 120 minutes. As far as the spaceship is concerned, no, it took 60. And the answer is they're both right. If you had a stopwatch running on the spaceship and you started it when the flash of light started and you stopped it on the last flash of light, you would say, 60 minutes. If you had a stopwatch running on the Earth and you started it when you saw the first flash and you stopped it when you saw the last flash, in this situation, you would say, no, 120 minutes. If 2 events are separated by 6 minutes according to the spaceship clock, they will be seen on Earth to be separated by 12 minutes when the spaceship is receding, that's the fancy word for going away, at a very high speed. By a very high speed, I mean 95, 98% of the speed of light, really fast. And by only 3 minutes when the spaceship is approaching at a very high speed. A dramatic illustration of, we call this time dilation, that time is not the same for one situation that's moving relative to another situation. You can illustrate this with identical twins. One twin astronaut, I'll say A for astronaut, who takes a high speed there and back round trip in the galaxy on a spaceship, while his other twin H, stays at home. When the traveling twin returns, he's younger than the stay-at-home twin. How much younger depends on the relative speeds involved. Okay? So here's our lovely little picture saying what's going on. We're going to apply this doubling and halving of flash intervals to the twins. Suppose the traveling twin recedes from the earthbound twin at the same high speed for 1 hour and then turns around and returns for 1 hour. As far as the astronaut twin is concerned, it's a 2-hour trip. What happens back on Earth? Let's find out. Follow this line of reasoning. The traveling twin takes a round trip of 2 hours, according to all the clocks on board the spaceship. But I'm going to, spoiler alert, it will not be seen to take 2 hours on the Earth. We're going to walk through the mathematical argument here on the next page. So what we're going to do is we have two identical wristwatches that are synchronized at the beginning. The first column is the ship leaving the Earth. The second column is the ship approaching the Earth. And let's just do the math. So the spaceship is going to send a flash out every 6 minutes. Every how many minutes? So ready? We leave at noon. Flash, 12:06. Next flash, 12:12. Flash, 12:18. I gave you the notes, right, Braden? I did?
Yeah.
Yep. Flash, 18 plus 6, 24. Flash, 12:30. Flash, 12:36. Flash, 12:42. Flash, 12:48. Flash, 12:54. Flash, instead of 1 o'clock, I'm going to call it 1300 because that makes the math easier. And now the ship turns around. So up till now, it's been heading away from us. Now it turns around and comes towards us. Scooch over all the way over to this column here. Now we're coming back. So this is still the spaceship. It's the third column over. Flash, 13:06. Flash, 13:12. Flash, 13:18. Flash, 13:24. Flash, 13:30. Flash, 13:36. Flash, 13:42. 13:48. 13:54. The spaceship now lands. The astronaut runs out to meet his twin sibling or her twin sibling, checks their watch, and the astronaut's watch reads 1400 hours, 2 p.m. Okay, that's for the traveling astronaut. Now let's repeat this experiment for the astronaut who stayed at home, their twin sibling. Okay? So let's go to this column. Now, while the spaceship is heading away, the flashes arrive 12 minutes apart on the Earth. So the Earth sees the first flash not at 12:06, but at 12:12. Flash. And then 12:24. And then 12:36. Flash. Flash, 12:48. Flash, 1300 hours. Flash, 1312. Oh, another flash, 1324. Another flash, 1336. Flash, 1348. And then 1400. Now the spaceship has turned around. It's coming back towards the Earth, which means each flash has less and less distance to travel. So instead of arriving every 12 minutes apart, they're going to arrive every 3 minutes apart. So this next flash arrives at 1403. And then 1406. Flash, 1409. Flash, 1412. Flash, 1415. Flash, 1418. Flash, 1421. Flash, 1424. Flash, 1427. I said 1227. 1427. Hey, my twin is landing. I'm going to go hug my twin. What time is it? Oh, I got 1430. What time is it on your watch? 1400. The twin back home on Earth has aged 30 minutes more than the twin who traveled. And this isn't a math trick. The twin back home on Earth, Rachel, experienced 30 more minutes of time passing than the twin on the spaceship did. This is how the universe works. Oh, and if you want to have fun, instead of making this minutes, make it years. The twin would arrive home and his twin sibling back home would be 30 years older than the twin who was on the spaceship. This is how the universe works. This is how, if we do eventually come up with near light speed space travel, it'll be one way. You're not going to want to come back and find, oh, Earth is 30 years older and everyone I loved that was my age is gone. And we can exaggerate this even more if you want. As soon as one object is moving relative to another object, they are experiencing time differently. My right hand on your left, my left hand on your right, my left finger is experiencing time differently than my right finger is. It is. Not by much. We'll calculate that eventually. We'll show you how to do it. But it is. And as soon as you start going fast, those differences become magnified. Why? Because the speed of light will always insist that you measure the same answer, that you get the same answer when you try and measure its speed. And the only way that can occur, well, if speed equals distance over time, weird stuff is going to happen for space and time to give you the same V. There is an equation, and that's going to be the next lesson. I'll teach you the time dilation equation. We will reproduce Einstein's famous paper. So, is it possible to travel through time? Yes and no. Special relativity tells us that we can travel easily into the future. The astronaut has traveled 30 minutes into their sibling's future. But we don't think you can travel into the past. Although, because I know you're going to ask, Mason, in a couple of lessons, I'll show you maybe, possibly, a theoretical way that maybe we could travel into the past, but it involves towing a wormhole near a black hole, so unlikely. But it doesn't currently violate any of our current physics laws. Put your pencils down, look up.